Right triangle has a right angle. After we went through every single right triangle having a right angle, then we also were able to define one specific part of the right triangle, and it's always in the same spot. The hypotenuse. That thing. The hypotenuse is always, 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 always across from the 90-degree angle. It never changes. It's always going to stay there. What happens with trigonometry, it's always about perspective. When you're at one angle, you have an opposite. When you're at the other angle, the opposite is a different angle, or a different side. So trig, I always like to define it as about perspective. So I'm going to introduce you guys to a couple of different ways that we do things in Algebra 2. When we talk about angles, we don't usually call them x anymore. We talk them in terms of what's called theta. You ever see that?
Yeah, the circle with a zero here. Or the,
yeah. All right. So we use that. So it's called theta. Whatever, it's theta. And you guys already mentioned the circle. Just draw a circle and do that.
all right.
It's kind of like your Shrek head without a Shrek head. So the way that I work with trig is kind of like generic, right across the board. Those of you guys who were in here in Flex, I was helping some geometry students, and I do it the same way with those guys as I will in here. I always like to circle an angle. Yeah.
I totally forgot. I got something for you this weekend, so I left it in my locker. So when we're done, can I grab it?
Sure.
Okay.
Okay. If I circle the angle that I'm at, the way I like to do this is that if I do a little dotted line, what does that point at? The opposite. So that means this is the opposite, therefore this is the adjacent. Okay, good. So if I can do that, I can list out my trig functions for that angle theta. Remember, when we're talking about our trig functions, we're looking at sine, cosine, and tangent. So what is the sine of theta? Good. Opposite of a hypotenuse. What is the cosine of theta? And then last but not least, the tangent.
So wait, what's adjacent over opposite?
I lied.
What is adjacent over opposite? Cotangent. I'm going to talk about that in a second.
Yeah.
So, secant destroy. The three standard trig functions are sine, cosine, and tangent. What happens is that there are what you call inverse trig functions. The inverse trig functions are defined as these three trig functions as their inverse. When you take an inverse of something, basically what you're doing is you're taking 1 over sine of theta, is you're flipping it around. Instead of saying 1 over sine of theta, we call it something different. This is called, the inverse of sine is cosecant. And all you do when you take an inverse is you flip the fraction. So if sine was opposite over a hypotenuse, cosecant would be
Hypotenuse over opposite.
hypotenuse over opposite. Now, for right now, we're not really worried about solving for the angles or anything like that to start out with. We'll use cosecant, secant, and tangent later on, more so in chapter 14, when we work with some of the trig identities themselves. Okay? So you have sines inverse is cosecant, cosine's inverse is secant. So the inverse of adjacent over hypotenuse would be? Yep. All we're doing is just flipping them around. What you might see in this chapter with this stuff, and I'll give you an example here in a second, and then cotangent is the inverse. That's what they call it, cotangent. What they might do in this chapter to start out with is just say that your secant of theta is 5 over 2. If they say that your secant of theta is 5 over 2, that means 5 is what on the triangle? It's the hypotenuse. And 2 would be the adjacent. So if this is theta, that means this is 5 and this is 2. Could you solve for this guy then?
Yeah.
That's basically what you might start out with, okay? It's not going to be anything yet, where we have to worry about our angles and things of that nature. We worry more about the angle measurements once we get into using the unit circle. And that becomes a whole different ball of wax later on. Okay? Question on that at all? That's really these three terms, you might have heard of them before. Did you guys talk about those last year? Okay. Really, that's all, for right now, that's basically all we're going to look at, okay? So what'll happen here is that we're going to use these things just within special right triangles a little bit today, and then go from there. All right. Speaking of, do you remember special right triangles?
Yeah.
What were they?
30, 60, 90.
The special right triangles are the 30, 60, 90, and the
45, 45.
your triples were just triples. Okay. So let's look at this. If I have trig functions of specials here, this is where everything. This is where the unit circle gets developed. What happens here is we're going to look at your special right triangles, and what I want to do is go over with you guys the algebraic ratios of their sides and see if you remember the shortcuts to solving these. Which one's which?
The hypotenuse is x squared over 2.
Good.
And the other ones are x.
Good. So what happens here is that the way that I set this up, again, it's going to be a little bit different than what you might have seen in the past. I set up this generic algebra setup where I know that across from the 45 is x, the other one is x, and this is your x squared root of 2. And basically what this allows me to do is set up some really easy algebra problems. For example, I remember last year, when you were in the stuff last year, you probably didn't mind if you were given that side on our 45, 45, 90. Because what's the other side? And what's the hypotenuse? 8 root 2. It was very easy. You just knew to do that right away. What happened is, let's say you were just given 8 as the hypotenuse. There's no root 2 built into it. And you had to solve the other parts. By setting it up like I have here with this little algebraic jig, if you want to call it that. What's that? It is. And I'm showing how this works out real clean here, and then you see if you remember the shortcut. You probably remember the shortcut. There is a shortcut. Does everybody agree we go opposite to 90?
Yeah.
So I would set this equal to 8. You agree?
Yeah.
So basically then I have a one-step equation to solve for. I'd have to divide both sides by the square root of 2. You agree?
Yeah.
So x would be 8 divided by the square root of 2. And we all know we don't like radicals in the denominator. You have to rationalize. What do you multiply top and bottom by? What's the square root of 2 times the square root of 2? 2. So 8 root 2 over 2 is? Okay. Do you remember this? Cut it in half and slap a root 2 next to it?
Yeah, that's
So this usually work for everything?
Yep.
Always?
Always.
But like, I didn't realize that was just like hard. That's how you solve it.
You didn't know that? Cut it in half. Slap a root 2 in it. What's half of 10?
5.
Slap a root 2 next to it.
Oh.
Just snap it.
Seriously.
Face.
Works every time. What if it is 15? What's half of 15? So it's 7.5 root 2.
You're lying.
So you're basically multiplying by
You're
2.
lying.
So basically, if you're writing that out every to make a geometry.
Okay. There's also when you're working with the 30, 60, 90s. What were the pattern of the sides for the 30, 60?
The short one is x,
Okay.
and then the hypotenuse is 2x, and then the other side is x root 3.
Good. This is defined out of an equilateral triangle, and we had the x root 3, and the 2x. And again, when you set these things up, the trickiest one was always if you were given opposite the 60, and it didn't have a root 3 into it. Let me show you an example. Let's say opposite 60 now is 9. Again, what I'm going to wind up doing is setting that part, the x root 3, equal to 9. Which means I have to divide by the square root of 3. and then rationalize. Remember, when I'm rationalizing my denominator, I'm multiplying the top and the bottom by the same thing. Square root of 3 times the square root of 3 is? So you get 9 root 3 over 3, which is 3 root 3.
Triangle isn't the scale.
No, it's not. Don't worry about it. My drawings never are. What did I do here? What's the shortcut?
Divide by 3.
Yeah. That's it. Cut it in a third, slap a root 3 next to it. It works every time.
Fancy, huh?
Okay? Notice, what's 9 divided by 3?
3.
Slap a root 3 next to it. Yeah. Okay? Now, the other thing that happens here is it doesn't matter if there's weird numbers or not. If this was 20, 20 over 3 root 3, it would become, oops, didn't erase out. It would be 20 over 3 with a root 3. Or 20 root 3 over 3 if you want to write it like that. Works, it's fine. If this was 20 root 3 over 3 for across from the x, what do you have to do to get it across from the 90? Okay, what's 20 times 2? 6 becomes 40 root 3 over 3. That's it. Remember, once you solve for the basic value across from the 30, all you do is double it. It doesn't matter how crappy or crummy the number looks, you just double it. It works. It's a nice little shortcut. Okay. Vaguely remember that stuff? Yes, sir.
Wouldn't the hypotenuse just be 40?
No, because you're doubling it. Because what happens here is this is the value of x. Oops. My value of x is 20 root 3 over 3. When I double that, I get 40 root 3 over 3. Okay. That's why I use this nice little jig. It's clean. Okay. Now, the real big important part of working with the specials is that using the special right triangles to develop all of the trig functions. So let me look at this. If I go back to the 45-45 to start with. If I go back to the 45-45-90 and I call my side lengths 1, what's the hypotenuse?
1 to the or 1 times the root 2.
Right. Are we okay with that? Right. So here's what I want to do. I want to list out the trig functions for 45s. So I want to list out the sine, the cosine, and the tangent. Do you remember from last year if you guys ever worried about the 90-degree angle with trig functions?
No.
It's all messed up sometimes. Okay. Again, the reason we don't worry about it is that, when, for example, if I wanted to know what the sine of 90 degrees is, the sine of 90 degrees would be the opposite over the hypotenuse. Well, if you're at 90 degrees, isn't your opposite and the hypotenuse the same thing? Okay. What if I'm looking for the cosine? What's my adjacent? Don't you know? It could be either side. It doesn't tell you. Okay. You don't know what your tangent is because you don't know which side's opposite or which one's your adjacent. Okay. So that's why we don't mess with the 90 degrees. Okay. We really don't. We will mess with the 90 degrees later on when we get into the unit circle. Because if I start here at 0, this is 180 degrees, that's 90 degrees, 270. You agree?
Yeah.
Okay. When I go around like this is also pi, and this becomes 2 pi as you get all the way around one revolution. What's halfway between pi and 0? Half pi. So it's pi over 2. Okay? What's going to happen here is we're going to start working with stuff in terms of radians, which is going to allow us to work through, there's going to be sets of ordered pairs that make this stuff work. Okay? And we'll get to that. I just wanted to get you guys an idea of where this is going. Okay? So if I'm at my 45, and I want to know what my sine is, what's the sine of 45?
1 over
1 over root 2, otherwise known as, rationalize it. What do you get? Root 2 over 2, good. What's the cosine? Root 2 over 2. Same thing, isn't it? What's the tangent then? 1, good. Now, let's look at the inverses. The inverse of sine is cosecant. So my cosecant then of 45 is the inverse of that. What's the inverse of 1 over root 2? Root 2 over 1. Do you have to put it over 1? Nope.
Not if you don't want it.
Secant of 45 is also root 2. And what would the cotangent? What's the inverse of 1? 1. Again, one of the reasons why we're going into this is that as we build into the unit circle, we use these as ordered pairs on the XY grid. And it will all make sense next week. All right, I'm just going to get you started. So, if opposite my 30 is 1, what are my other two sides?
2 and
Where does the 2 go?
hypotenuse.
What's the other side?
Root 3.
Okay. Take a minute and figure out then what's the sine of 30, cosine of 30, tangent of 30, sine of 60, cosine of 60, and tangent of 60. Take a second to see if you can fill those out. If you get rambunctious, go ahead and write out their inverses too. What did you guys get for the sine of 30?
1/2.
1/2?
No. I got 1/2. Now I feel stupid.
Yeah. What's the cosine of 30?
Wow.
3 over 2.
I just drew my picture wrong, that's all.
What's the tangent of 30?
3.
Very good. Everybody agree so
How
far?
do you do that?
What?
How do you rationalize?
Yeah, I don't get that.
All right. When you have 1 over the square root of 3, in order to get rid of the radical in the denominator, you multiply by that same value. But what you're doing here is by multiplying top and bottom of root 3, what's root 3 divided by root 3? 1. So I'm just changing the shape.
But you only multiply the top part.
No.
That's why I was confused. That was
Okay. Does that make sense now?
confusion.
Now, excuse me, sine of 60 is what over what?
Oh, Murph. Slow down. Sine of 60? Root 3 over 2. Oh, we're doing. Oh, I was doing the.
Okay. Are you okay on that?
Wow, I got it. I didn't read the second part very well.
Again, what we're doing here is when you are working with trigonometry, if you're working with a specific angle, if you're still having problems setting them up, circle the angle you're working with, draw across, which one's your opposite, label your hypotenuse, and then just fill them in. And walk through them like that. All right, that's just basically what we're looking at doing here to start with, guys. Just real straightforward. I pretty much can guarantee by the end of next week, you're going to have all those memorized. They're that common. We use them all the time. It just makes life so much easier to know those. Okay. Plus, when you graph trig functions, it makes life easier. And that builds us into solving right triangles. Now, when you're working with a right triangle, how many parts are in a right triangle?
There are 6.
There's 6 parts. In that right triangle, you always know one of them. What do you know?
The right angle.
Okay, so that means you have to know. I'm really afraid of this.
It's actually not the bag.
Okay.
It's a
Now,
round thing that Jim splits.
one of the things that you will always know, in a right triangle, you always know one of the angles. Since it's a right triangle, you're going to know that you have a right angle. That means how many parts are left?
2.
5. 6 minus 1 is 5.
Oh.
So now in this,
count the sides.
in this problem,
You do the sides of
take your calculator off, you can't do that one in your head.
I don't have a calculator right now.
Bad. Now you'll notice that you're probably going to be given 2 of the sides.
You're killing us, bro. Come on now.
I know the 20 and I know the 12. I cannot stress the importance of this next step enough. When you're going to solve out the rest of the triangle, please try to remember to reuse your given statements. There's a reason here. If I know that I'm given the 20-degree angle to start with, and I draw across here, 12 is the what?
Well,
The opposite.
The opposite.
Which means this is my adjacent and this is my hypotenuse. Okay? Finding angle B is a piece of cake. What is it?
70.
70.
Yeah.
All right, everybody agree that's 70.
Yeah.
Again, 180 degrees in a triangle, take out the 90 you're left with, 90.
Oh yeah.
So if I want to work with my opposite, my angle, to find my hypotenuse, what trig function works with opposites and hypotenuse?
So.
Science, yeah, so, very good. So I know that the sine of 20 is 12 over c. Do you remember the trick when your variable was in the denominator? What was it?
He doesn't know.
I know, right?
I do know it. Switch the sine 20 with the c.
Very good. Anytime your unknown value, guys, is in the denominator, all you do is switch these two out. C is going to be 12 divided by the sine of 20. Now, Richie, I know you didn't bring a calculator today. For shame. But you can do all of your work up to this point.
Do it in your
I
head,
did
Rich.
actually.
Okay? Because right now, he's telling me that the C value is going to equal 12 over the sine of 20. Now, type your calculator. Do you guys know how to check the mode on your calculator?
No.
Yeah.
Hit the button that says mode. In these first few sections, we have to make sure our calculators are in degree mode. Everything we're doing here today is all in degree. Mode, it's in the kind of in the upper middle.
Yeah, that's in degree.
You want to make sure it's highlighted where it's degrees. You might have to move it over to highlight it.
Oh, I was on radian.
Yeah, these things are defaulted to radians.
That's not good.
So for those of us that have dropped our calculator, batteries might have fallen out once or twice. When you put that back in, it'll probably default back to radians. So just make sure that whenever you're using trig stuff, if they're talking about things in degrees, make sure your calculator's in degrees. Otherwise, you might get some really, 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 really crummy answers. You might even get negative values. Don't want that. So all you have to do is, I don't know why this is.
No.
Anyway, so my calculator has to be booted. In this case here, when you take 12 divided by the sine of 20, what do you guys get for C?
35.085.
35.19.
Okay.
Oh.
Now, what trig function is going to allow me to, using my opposite, to get the adjacent?
Opposite over adjacent.
Tangent.
Tangent, very good. The tangent of 20 is 12 over b. Again, whenever your variable's in the denominator, you can just switch them out with the trig function. It's a nice shortcut. Now, I do want to stress, did you guys notice how I reused my givens for both of those? Try to redo your givens, guys. The reason that I'm saying that is, what happens if you mistakenly typed in your calculator sine, or 12 divided by the sine of 22 by mistake? Then your hypotenuse is wrong. If you use the Pythagorean theorem to get that other side is going to be wrong no matter what. But if you typed in something incorrectly to find the hypotenuse, reuse your given, you could still have the possibility of getting this right. If this is wrong and you reuse it, the other one will be wrong, no matter what. Okay? Is that wrong? No. Okay. You kept looking up and down like I did something, something was typed in incorrectly or something. I was just making sure you're all right. Because, you know, I've never made a mistake.
No.
Okay? Also, I would like you guys to get in the habit of writing out what you're doing before the calculator. I don't know if it was in this class or one of the other sections that did that on the log test, where they wrote out what they were about to type in their calculator, but got the wrong answer. But I gave it to them because they had all the work correctly. You might have just you transposed a digit or something along those lines. I don't know, I really don't remember if it was this class or not, but that's a great habit to get into, okay? So it only takes a second. So for those of us that don't have our calculators, we can actually do all, thank you. We can actually do all of the work that we have prior to doing anything else, okay? Questions on any of that?
Yes, I do.
Let's briefly discuss one other bit here. Do you remember angles of elevation and depression?
Yeah.
Okay. Do you remember how they were developed? Those aren't straight.
Looking at stuff.
Looking at stuff, yes. If these two lines are parallel, the angle of elevation is the angle from what you're horizontal looking up. Horizontal looking up was your elevation. It's your angle of elevation. The angle of depression would be the alternate interior angle of that. And that's the angle of depression. Those two angles are congruent. We use angles of elevation and depression usually within word problems. For those of you guys that did this last year, remember last year when you did that clinometer, that clinometer experiment where you guys were looking through the straw with the protractor? Yeah. That you guys used basically, you were using angles of elevation and depression. You were using tangent over and over and over again with something like that, and it was magic. Yeah.
Did you set that up, Mark? Was that you?
Seb and I actually did that for a lesson while we were in college. We wrote that experiment. We did that as far as a project we had to do for one of our classes, and we've used it basically every year since then. Since you and I have been here.
You went to Oxford?
What's that?
You went to Oxford?
My wife did.
Really?
Yeah.
Isn't Oxford overseas?
In angle. That's my angle symbol.
Mark, isn't that in
England? Yeah. My wife did a semester at Oxford University. Yes.
Really?
Yeah.
Could you say she went to England?
Angle. That's Matthew.
It's not even close. It's
Oh,
just
yes, it is.
For example, remember this is not drawn to scale.
What are you drawing?
It's an airplane.
England.
Oh, that was like a funny one. That was like
It's an airplane. And here's the tower
Good job.
with the giant radar dish.
That's so
Yeah,
Is that a giant cup of soda?
There's the door, and here's the windows.
Still
It's
see-
the radar station. The tower. It's horrible.
That's a drink with umbrellas. Yeah.
It's offensive to drinks, thank you. The airplane. The airplane is, I don't know, 40,000 feet up in the air.
Oh, why is it 40,000 feet if it's that close to landing?
Not to scale.
Yeah, the building's big.
Are you trying to hijack a building right now?
Leave me alone. Not to scale. I am now absolved of bad drawing.
I want to highlight that.
Never heard that before.
Again, let's say it has an angle of depression to the base of the tower.
But why aren't you crashing into the tower? What is
It's not crashing into the tower.
Why?
Just,
It's landing next to it.
Lord, let's say it's 17 degrees.
You're taking it too
How far is the base of the tower to the vertical height of the airplane? Again, what you're solving for here is this horizontal distance.
Wait, is that diagonal length 17?
What is
No, what I said here, the angle of depression is 17 degrees, which means what's the angle of elevation? 17. What trig function are you going to use to figure out that horizontal distance?
So,
You need a pulling thread?
do you know that that's...
Oh, yeah.
So-
Yeah.
Thank you. This is the opposite. This is the adjacent. Use tangent. You had to explain it, sorry. In this case here, usually I probably would guess if you have angles of elevation and depression, 9 times out of 10 you're probably using tangent. Okay. So you have the tangent of 17 is 40,000 over something.
It's 40,000?
Yeah.
Oh my goodness.
And that's what you're setting up as. Okay? I don't know what the answer is. 134,834?
That's unrealistic.
Check and see if your calculator's doing radians. You'll be in degrees these first few chapters, or first few sections. It's all gonna be degrees.
How many miles is that?
Divided by 5,280. Well, this is about 8 miles, and that's almost 2 times, double, 3 times it, so it's 9, 10 miles.
It says 24.
It'd actually be 17.
Oh, whatever.
Oh, it's 3 times.
Yeah, you did like
Second.
get normal for myself running the class from like that server and actually do.
Let me give you some problems. This is on page 4 something or another. Oh, it's right away.
Or something or other. I have one older brother. Hey now. Mr. Mark, Jack is cracking jokes. Unruly jokes. Bad.
On page 772, I'd like you to do numbers 20 through 24 and 37 through 51. One quick reminder, there is a problem in here where you have to find the area of a regular polygon. Do you vaguely remember that formula?
Yeah.
Is that something with the little
Awesome.
Apophone.
Oh yeah.
Awesome.
It's a possum.
Is it like 1.5? Oh, awesome.
Yeah, the area is 1/2 perimeter times the apophone. You will, there's a couple of problems like that. You have to remember how you set that up. You'll be working with the a regular polygon. I want to see if you guys remember how to work with those angles and how you set through on there. Okay? Well, try. Okay?